Have y'all been on the YouTube channel? Watch the PowerPoints?
I opened it, but I didn't watch it.
Okay. I'm trying to grow my followers. All right, so we've been picking up with, remember we've been talking about these two types of adsorption. Outer sphere, where we have this water molecule that's adsorbed to this oxygen on the outer edge of that clay material. And then we also have this phosphate that forms a covalent bond. So outer sphere is an attraction like a magnet. Inner sphere is they're locked in because they share that covalent bond. No direct chemical bonding. It's the electrostatic. It's where you rub the balloon against your head, put it up against the wall. Eventually that will stop. We discussed some of the things that that were affecting our outer sphere complexes: ion hydration, the valence, the concentration, and this is responsible for our CEC. We kind of went over the diffuse double layer. Everyone's favorite, the three sources of pH-dependent charge are?
Iron and aluminum oxide.
Oh, iron and aluminum oxide. Broken edges of clays. Functional groups of organic matter. So as we add lime, we increase the hydroxyl concentration. Those hydrogens dissociate from those functional groups, form water, leaving this negative charge. So we had this reversibility where it's 1 for 1. We have charge equivalence where we need two hydrogens to dissociate or to exchange with one calcium 2+. Inner sphere, that covalent bonding where those outer orbitals share an electron in there, and then they're finally balanced. When we think of inner sphere, we're going to think mostly of our anions or oxyanions that have some some oxygen on there. You might not mess with beryllium, but you might encounter lead somewhere in your thing. So just remember that it's going to require more energy to break that covalent bond because there's some inner sphere adsorption. And that's also going to be dependent upon the ion solubility and the ionization energy. As I was looking through all the notes, I'm like, you know what? I would drop this class if someone put that on the board. Like this, some calculus, just a mess. And then the ability to form those bonds, and then also the properties of the clay. So the broken edges of clay, is there any organic matter? And are there aluminum and iron oxides in it? Because of pH-dependent charge, functional groups of organic matter. Broken edges of clays, aluminum and iron oxides. We can have some adsorption of these non-ionic chemicals. We have hydrogen bonding for organic, and then inorganic, we have the covalent bonds with those functional groups. Desorption is just where that molecule, anion, cation, breaks free of this charge that is holding it to, whether it be electrostatic from outer sphere adsorption or chemisorption where it's the covalent bond, but that is broken and is released into the soil solution. For this interlayer collapse, where we have these 2-to-1 layers that have some water come in, move in between the middle of those two layers, and potassium is in there, becomes adsorbed to this tetrahedral layer through outer sphere absorption, but then the water is removed from that system. The plants use it up, and because potassium fits so well inside the void that is made from the lattice structure of illite, of the tetrahedral layer. Now we have two of these two tetrahedral layers, and so it fits one half, just like you would have a ball joint. The top half fits in the top half fits in here, the bottom half fits in there, and when that water leaves, and that potassium is fixed, and then also ammonium fixation, because potassium and ammonium are about the same size and also the same charge. Precipitation, that's when we were talking about trying to get metals, and then also if y'all can remember back to the phosphorus cycle, that we have this precipitation and dissolution. It just cannot remain in solution long enough because of some chemical attraction, and it precipitates out. Mycels and supermolecules, a whole different ball game. And so once I got to like right here, I realized that as we're about to jump into this book, that no one's had to calculate ion concentration or ion activity or the Debye-Huckel or calculating how big the diffuse double layer is. I think what we need to understand and know is that it's there, and that there's going to be some movement back and forth. None of y'all are ever going to calculate that ever again. So this is new information, as in it's new information from this presentation or this module, but it's not new information than what we've been talking about. Cation exchange, these are going to be our base cations. Y'all remember that from soils? And then our acidic cations are going to be what does pH measure? Hydrogen. And then there's a couple of other ones, but one primarily that we think about when we think of acidity. Do y'all know about azaleas? Aluminum. So aluminum and hydrogen. Yeah. I'm asking y'all a very simple question. It's not a trick. I'm not here to trick people. I want you to come with the very first thing that comes out of your brain. Like, is it aluminum? Yes, say that. It is the sun. That is exactly where we get our heat from. And I want to try and make sure that we get that sort of thought process, because you do know. You do. I know you do. It just takes a second to get it out, and then there's this fear of, what if I'm wrong? And it's okay. Also, you could have looked at pH decreases. We have aluminum and hydrogen. Acidic soils, alkaline soils. Everyone good here? So the way that we measure the CEC, now remember this from soils, maybe some other classes that you might have taken with me. They'll sum the base cations, and that will be the cation exchange capacity. Agreeable with that statement, because the CEC would also measure the the aluminum and the hydrogen as well, because they're also cations. And then there's another method where they will saturate the soil with an index cation, like sodium. And if y'all remember from soil, sodium will take up each one of those charges. We can flood the system with enough sodium that the charge, it's kind of like going into battle. We have so many sodiums that they outnumber any other charges. And that concentration is so much, and that's what they'll calculate. Someone in a chemistry lab over in Prescott will calculate how much sodium they need to add in order to displace all these cations. They're over there doing the Debye-Hubbell. They're over there calculating the ionization. So that sodium introduced into the system, or even calcium, now we can use half as much because we have twice the charge. So you add sodium to the system, it displaces all the cations, they come out in the solution, and you can measure that. Then we'll come back and we will displace them with either potassium or ammonium, and we know the concentration of that. We can measure how much did not come out, how much ammonium did not come out of that system, and they can determine the CEC that way. Back now. So right here, we add ammonium that flushes all of our cations out into the solution. Ammonium replaces all of those cations on the exchange sites. We measure how much calcium, magnesium, hydrogen, aluminum, all those other things that came out. And then we will displace the ammonium with potassium, and we can measure how much ammonium didn't come out. So it's kind of just we added this much, this is what came out. Not so much that you would need to be able to regurgitate that or on a test or anything, explain the process of how they measure CEC. Just to understand that they're going to displace or cause there will be a desorption of those cations off of the exchange sites because we added this strong ammonium solution. They typically do it with ammonium acetate, and that's enough to displace everything. They can measure how much ammonium maybe was in here versus what's in there. And all they're doing is they're just basically flushing the soil out with everything that they have. All right. All right, let's start right here first. So the way we're going to calculate the CEC, y'all remember this from soils? Y'all are totally good with this? You'd like to see this one more time? All right.
Yeah, I'm just saying let's not get overconfident.
What's that?
I was going to say let's not get overconfident.
That's cool, but I want you to be confident when you leave this class.
Yeah.
That's what's more important than anything that I'll ever teach you, is that when you leave here, that you are confident. And I don't care if we have to go, and if I have to reteach fertility, I will. But I want to make sure that you do know what you're talking about when you leave this class. So the sum total exchangeable cations that a soil can absorb, which is the sum of all this. So we have 130. So for soil A, the CEC is 130 centimoles of charge per kilogram.
It's probably different.
What's that?
I think our far's different.
They are different.
Well,
I'm teaching, and then y'all will do. So we summed everything. What about for soil B? What is the charge for the CEC for soil B?
29.
Everyone agree? 12, 20, 4, 5, 29. All right, and so then what is the percent base saturation? Remember what our acidic cations are. Aluminum and hydrogen. So if we take 130 minus 70, we're taking these two out of the equation now. So that's 60 divided by 130. Huh?
Is it 55?
60 divided by 130.
46.15%.
And of course, then we're going to multiply that times 100, get percentage. Correct? Everyone saw that? Super simple math. And so now what about for soil B? You did that with 12 divided by 29?
Yes.
41.38%. Which one of these soils do you think has more clay content?
It would be the A, right?
Soil A. Because this one doesn't have a very high CEC. High CEC. So when you're looking at your soil test and they tell you what the CEC is, you can kind of determine what your soil type is. And we'll look at that in just a moment. So on your papers, the best thing to do is to add up all the CEC first. And I think I taught this a little different in soils. If you want to, you can go across that and calculate the hydrogen and the aluminum, and then calculate the bases, and that should give you the total CEC. And math is communicative, distributive, and associative. So you can add the CEC, subtract the amount of aluminum and hydrogen, and get the bases. It's just repetition. All it is, just repetition and doing it again and doing it again. Y'all, I sat through all these classes, a whole PhD, and I was like, y'all telling me the same thing I already knew. I took plant breeding and seed production and plant growth and development all in the same semester. And every time I went to class, they talked about the exact same thing that we talked about in the class previous to it. So it was actually pretty cool because I knew what you were talking about. It all made sense, but it took all 3 of those classes to get that information into my brain. Y'all got them? Did you remember doing that from when, who'd you have for soils? Rick? You had me, so I know you remember doing this. Did y'all do something like this? And Dr. Branson, because that's actually her material. Okay. I just wanted to make, and like that's the thing is I don't know what's been taught, what hasn't.
It's been a while, yeah. That was something I remember and actually understood with him pretty clear.
Yeah.
The rest of it, yeah.
Like, man, that's part of the thing. Like, I want to make sure you know. And I'm going to teach you a whole bunch of stuff you'll never use before, or we can hyper focus on the stuff that you will absolutely use on more than one occasion in the same month. Like, it's different for me coming from Mississippi State because, man, they teach you every possible thing that professor knows. And you go, you know what, man, I've never once had to calculate ion activity. We're not doing soil chemistry. Like, in the lab stuff, we're not doing that. Y'all are going to get out and go work and need to do some more practical applications. And I'm going to try and curtail this class more to the things that you're like, you know what, now that's actually useful. Not calculating some square root of some exponent. That's crazy. All right, how we do? Nathan? Killed it? Cool. It's just repetition. Just repetition. Okay. So, y'all remember that I was talking about that, like, some of this stuff has a role in herbicides. You may apply a herbicide and it may or may not work. Or there may be some desorption. It's supposed to have some strong soil adsorption. Something changes in the soil and it kills the crop. And so here was an illustration that this wheat field was sprayed with this chemical, and there were 3 spots, maybe even 4 back there, that the herbicide didn't work. And you go, how come?
Kind of low CEC and like the stuff not herbicide and attack.
Correct, except it's the opposite here.
There's a high CEC was in the subsoil, so it didn't reach down that far into the soil.
No, so what they did is they bulldozed those areas, and there was a clay pocket in there that had a higher CEC. So the CEC of all this stuff is what, 4? What did they say it was? This low CEC was 4 centimoles of charge per kilogram. But in these spots right here that got tilled up or got brought up as they scraped this land whenever it was, some of that clay came up, which is the difference between here and here. And so we have more there's more capacity to adsorb that soil to those exchange sites. Because remember, it could be organic or inorganic, and we have outer sphere or some inner sphere adsorption to that CEC. So anyhow, those are kind of some of the things that you might run into. And I'm really going to try and work towards more of the application side of this for the rest of this class. I went into this thinking I was going to be teaching like the soil chemistry I went through, and we're not doing that. So I'm going to try and get us to where we're doing more kind of, this is what happened. This is the situation. What happened? Well, the CEC, it could also be pH. So not only does it work in CEC, it also works in pH. Now we will go over that, where we're starting to get this. Have y'all ever seen the pKa of a material? Not so much? We will. And all the pKa is that at pH 6, we have equilibrium between the molecules of whatever it dissociates from into, so acids and bases. At pH 6, that is where you can expect there to be 50% of this type and then 50% of this species, I guess is the correct term. And if the pH gets to be too low than that, then you have a different species, not the one you applied. The pH changed the speciation of that. Now you applied atrazine, but the pH was wrong, and now you've applied some other chemical. You'll see it in just a moment. What's going on here? Already. Not gonna let me do it like that. Okay. Kind of a similar situation where we have what they did is they tested how much the absorption of kaolinite versus montmorillonite. Y'all have all heard of BT, right? It's what's in corn. It stops the corn borer, and it's a toxin. Remember, toxin being something that is produced from a biological organism. So what they did is they tested, they applied 500 micrograms of BT to these soils, and then over time, this is the absorption isotherm. So almost immediately, let's say what, I don't know, 20, 30 minutes, all of the BT was adsorbed with a D to this montmorillonite. So going back to the table, that's the 130 centimoles of charge per kilogram. The kaolinite, probably soil B on the right side, only had 30, 29 centimoles of charge per kilogram. But even though that still didn't adsorb only this much, roughly in about 30 minutes. So the reaction is quick. If the sites are available, they will be taken up by these chemicals and the charge associated with them. And then no more happened over the rest of this time. But because it was such a high CEC here, it was able to absorb almost 80% of what was applied. And on a herbicide label, it will tell you, you need to add so much more if you have this 12. If they had known about this, let's say all of this was 12, the CEC was 12. If they had known and looked at the label, it would have said to add a higher rate. And don't worry, there's some chemist, some geek in a lab coat, sitting down with a pen and a piece of paper, or some Excel spreadsheet calculating how many centimoles of charge there are, what the adsorption, the changes that are going to happen because of the pH. They take all that stuff into account, and then they say, we need to increase this rate by 2. need to put a 2x rate out of this chemical, or you need to apply the chemical twice. Maybe it's atrazine, you can only apply so much at a time. But they take that into consideration when you go to apply your chemicals. Also the same thing with lime. On a sandy soil, you would only need maybe 1 ton. But on a clay soil, you would need 3 tons. Because there's so much CEC that will take up that calcium and that magnesium that the chemical reaction won't take place because it's being held by the soil. Making sense? Again, there are chemists that are calculating these coefficients. This KD, this KOC, and they're just partitioning coefficients on what's going to happen. Partitioning coefficients D and organic carbon. So this is taking into account the partitioning coefficient of the molecule, and then this is taking into account the partitioning coefficient for the organic carbon, or organic matter. And so what they determined was that 0.013 grams of carbon per grams of soil, that the soil contained 0.013 grams of carbon. How they determined that was, someone still got their calculator open? Divide 1.82 by 140, and then multiply times 100. Huh? Yeah. 1.3%. So giving these, we can determine how much carbon was there, and that the higher the number, the KD, the stronger the absorption. So you add this atrazine, there's a change in pH, there's a change in CEC, there's something. We have a lot of organic carbon, and we get this breakdown, and now we have this hydroxyatrazine that's held tighter to the soil than this. So once this breaks down, everything will go to hydroxyatrazine. And that's where we get into pKa and some of those other things. The long and short of it is that atrazine will turn into different byproducts, secondary molecules. It has to break down, it has to decompose. It will, it's trying to get to equilibrium. And so we know how much of these secondary compounds and how much they're adsorbed with a D, adsorbed to the soil. That kind of makes sense of how our CEC and our carbon and our pH dependent charge are all playing together into this. It can really mess up something when you go to plan this out and the boss comes back and says, hey, what the hell happened? And you go, man, I don't know, man. I did all the calculations that Natchez told me, but we didn't take into consideration some of the other things that might happen. Might not have read the label extra, or a producer says, Nathan, man, you got to help me out here, dude, because, man, I applied it just like the label said, and how come it didn't work? And you go, well, what was the pH of your soil, and what was the CEC? Do you have a soil test that I can look at? Because that's going to give you some information about what might have happened. Or you can at least remove some of the possibilities of things that happen. Well, we know that the pH was okay. We know that you applied it at the right rate. All the CEC was messed up. The CEC. And that's why you have these 3 islands in your field that didn't work. You get a soil map and you go back and you look and see what the soil type is. And you go, well, you didn't soil in this little area, did you? And that's where all your highest CEC is. That's where all your clay, that's where your smectites and montmorillonites with this high cation exchange capacity is. And so when you sprayed over that, herbicide didn't work. Or when you go to apply a pre-emerge in the spring and it doesn't work, we have to figure out why. What was the cause? pKa, pH, CEC are going to be your top 3 things that you should start with in the lake. You remember seeing that, Nathan? It's been a long time, hasn't it? What's that? It's been a long time, hasn't it? That's cool. Go ahead, Michaela. You got it. If you know what you got, go. So I was laying in bed thinking about this last night. Like, we haven't talked about any of those processes, the 6 typical processes that we think about in soil chemistry. But the nitrogen cycle carries like technically 5 of them. And so I just wanted to reintroduce the nitrogen cycle to make sure that Nathan at least sees it and can understand it, because it's going to be important for everything else that we do in soil chemistry. If you can understand the processes that happen in the nitrogen cycle, you'll understand the processes that can happen in any cycle. And then what this is going to lead into, when we understand the processes that go on in the nitrogen cycle, we can start to develop and understand some calculations that we can do to be ahead of the curve, to know that if we apply fertilizer in the spring, how much material, how much lime do we need to apply in the fall. So we can start to calculate how much acidity I'm actually adding to my soil because of my fertilizer application. Got it, Isaac?
No.
It's okay. Hey, it's okay if you don't. It's okay if you don't. It's not a test. Again, it's just like the CEC thing and the base saturation. I didn't want to go back over that again. I want to make sure that you leave aware of the processes that go on in the nitrogen cycle. And I think once you see it, you'll go, oh, this makes sense. This makes sense. And you get to your job and you start going, well, yeah, here's what happened. This is where we got the acidity from. So I'm setting that up. Okay, it wasn't to go, you don't know, do you? I will never do that to students. God, I hated when my professor did that to me. He made me feel like an idiot. Man, I thought I was pretty smart until I met him, and he was like, yeah, you're a moron. You don't know anything about, you can barely spell your own name. God bless. Dude, cut me some slack here. Like, you can't talk to students that way. Like, they'll hate you and themselves. So, that's never the case. All right, y'all ready to look at these things? Move this up here. Yes, favorite. All of this stuff.
Oh, I got all but one.
Yeah, that's what's up. Michaela?
Yeah.
Yeah, you just didn't have to do any of this part, huh?
I just put fixation. I forgot to put NH4 on 7.
Where?
7. Up at the play. 2
Right here? Yeah, that's cool.
I wrote
That's
clay
okay.
fixation.
That's okay, because it was different, and I said clay fixation. I got 2-to-1. This is 2-to-1 clay fixation, ammonium fixation, and that's where I kind of had that issue with in class. Like, I might put ammonium fixation. In my brain, I was taught 2-to-1 clay fixation, and so let's start at the top. We have biological N2 fixation, which is we plant soybeans, we make sure that we inoculate them, and they will fix nitrogen from the atmosphere to form the nitrogen that they need. Here we have our immobilization and mineralization. And then within these, in fertility, we actually had to fill this in. So from soils, y'all just needed to know the basics. Then we have fixation, immobilization and mineralization, nitrification, leaching, bad for the environment. We have plant uptake. 4, we went over immobilization. 6 was leaching. It can be fixed in clays. Remember the illite with the potassium? It can also happen with ammonium. It can volatilize into the atmosphere. This is where you're going to apply granular urea to crop residues, and the producer is going to go, Nathan, you told me to put out 200 pounds of urea or 200 pounds of nitrogen, and I did, and it didn't work. Why? You go, well, you got crop residues, it didn't rain for a while, there's all these little things that went into it. It underwent urea hydrolysis, and when it did, the pH changed. The pH changed, and therefore now we have this dissociation of hydrogen from the soil into the molecules and all the stuff. And she just rolled her eyes.
Her brain hurts.
She just rolled her eyes, because that's what we went through in fertility. From the whole 9 yards, this is the most intricate cycle that you will deal with in agriculture. But once you understand this, everything else is a piece of cake. Dynamic, very dynamic. This is always changing at any time based on several things. And then finally we have denitrification. Got it, everything, Nathan?
Yeah.
I just want to make sure, man, I'm not leaving anyone behind.
No, yeah, I'm just looking at it.
Okay, cool, don't worry, we're going to go over it. So, the 6 processes that we had absorption, desorption, which we've kind of spent the past couple of class periods talking about, cation exchange, precipitation and dissolution. Not so much with the nitrogen cycle, but with the phosphorus cycle. So we have these secondary minerals that will dissolve. P will then adsorb to the C's, the AEC. It might precipitate out because there's too much. Immobilization and mineralization. The immobilization is inorganic to organic. I'll go back over this again and I'll show you exactly where each one of these happen at. Mineralization is organic to inorganic. I'm also prepping you for the test. Microbial and biochemically mediated. Oxidation and reduction. This is the one we're going to spend a little bit of time on, because it's going to, this is what is going to, and also this dissociation, this is what's going to contribute to our soil pH, which is kind of the next part that we're going to talk, kind of like the next module, the end of this module. And then finally, volatilization and gas dissolution, which is our volatilization and denitrification. Write these down. Sorry. You got adsorption, desorption, dissolution and precipitation. What was the other one that we had? Immobilization. Mineralization, we got oxidation and reduction. Complexation. can see where this immobilization and mineralization is, right? So that's a check. You can see that one in there. What about adsorption and desorption? Where would you think that the adsorption and desorption would occur? Right here at the soil surface. There's going to be some adsorption to this 2-to-1 clay in the CEC. So in here we've got adsorption and desorption. Check. We've also got some that is going to occur right here with our anion exchange capacity. We have negative. So what type of complex, what type of inner sphere or outer sphere complexes for nitrate? Fifty-50 shot. Inner sphere. My boss would give me those, and then I didn't care. I mean, because I was working for him when I was in his class, and he'd ask me if it was outer sphere or inner sphere, and I'd go, outer sphere. He'd go, wrong. I'm going to find an inner sphere. Correct. Like it's okay. It's all right. So we have inner sphere complexation here, and we have outer sphere while it's ammonium, right? So you can think the positive charge being outer sphere, and then inner sphere with our nitrate. But also remember that it's weakly adsorbed. So this, and it's also very soluble in water. So when we add irrigation and we have nitrate, where do you think it's going? Out the profile. Okay? So we have our leaching, which technically could be in dissolution. It will make it down. It will dissolve into the water. Okay, next. Here we have ammonium and nitrate in the soil solution that is held to our CEC and AEC, and it will be taken up by the plant. Okay? Where else are we at? Complexation and dissociation I'll get to because that's going to be tied in with oxidation and reduction. Here we have our oxidation and reduction. Well, this is actually the oxidation. We're going from organic. And remember, we have oxygen into the system, so that's how you know that this is an oxidation. And then finally, over here, we have a reduction, where we are reducing the electrons. Or the hydrogens, actually. It's actually gaining electrons. It's becoming more positive. Gaining electrons. Reduction of gains, oxidation of loses. Hydrogen. We're gaining hydrogens here. And then finally we have our volatilization or dissolution. So just in this one cycle, we have all of these things going on, and it's all really dictated by this microbial population. All right? Yeah, buddy. All right, I just want y'all to follow along with me. Man, we had to go over this a couple of times in order to get it down. So when we apply, so this is one of our hydrolysis reactions, which is part of dissociation. And hydrolysis means we are going to split water. Okay. We have our urea fertilizer that we apply to our field. It is not in a plant available form. Our two plant available forms are what are the two plant available forms of nitrogen? Look on your sheet. plant uptake.
NH4 plus NO3.
Ammonium and nitrate. 2 plant available forms. But we can't just apply ammonium and nitrate anymore because, you know, some people like to mix it with diesel fuel and blow stuff up. And so my professor told me, he's like, hey, call the co-op up and see if you can't get a ton of ammonium nitrate. I'm like, you know, what? Hold up. I don't know that's a wise idea. Hey, I work for Dr. Varco at Mississippi State. He told me to call up and see if y'all had any ammonium nitrate. And he said he didn't put it together, and when he would have Middle Eastern graduate students, he'd tell them the same thing, like, hey, call down there and call the co-op up and see if you can get some ammonium nitrate. And they always told him no, they didn't have any. So he'd have to go down there and, it's me, we need this. So we have urea and water that is going to form this intermediate compound of ammonium carbonate. We are going to consume 2, so we split water and formed a new molecule. We're going to consume 2 hydrogens from the soil, which is going to make our pH do what? It's going to go up. It's going to increase. So when the pH increases, what happens to the CEC? It increases as well, which is good for us. Which is good for us because we're about to have 2 ammonia molecules be released. Carbon dioxide and water, and we're talking like the little molecule of water, right? Like, so we went from had water, lost water, gained the hydrogens back, now we have water. This goes off as a gas, carbon dioxide, water remains in the soil, and we have ammonium that can now be attached to the CEC, which is increased because we've increased the pH. Because we've increased the pH, and remember, we're always trying to get to equilibrium, we're always trying to get back to balance. We now have this extra hydroxyl concentration in the soil and our water. To make this balanced, this hydroxyl will take one of those hydrogens from ammonium to make 2 water molecules. You see this right here? 1 hydrogen to make 2 water molecules. And then ammonia with an A, gas, that volatilizes. So based on just this exchange, we have a hydrolysis. We might have some adsorption and desorption. We have some gas dissolution, some volatilization of carbon dioxide, and then we also have a volatilization of our ammonium or ammonia gas. You apply this fertilizer in the wrong conditions, it undergoes the process because it has to. We've got to reach equilibrium, and in the process, the producer actually lost up to like 30% of the nitrogen that was applied. And they go, how come? You told me to apply. And you go, what? Well, wait a minute. Let's look at some other things here. There's some other things that are involved in this. But just that you can see we have this dissociation from a hydrolysis reaction, and we're still trying to form water again, but we have this volatilization. Next we have it the other way. So this is in the bottom where we had ammonification and then nitrification. And this is a very short form of it. We have our ammonium adsorbed to our soil. We introduce oxygen. Automatically, this is going to be an oxidation. Oxidation, it loses. And I always consider those as hydrogens. But anyhow, we'll form nitrite. We will release 4 hydrogens into the soil, which makes our pH acidic. Good job. Water, and then there's some energy. And we'll continue to do this another time. And so we have all these ammonia molecules. Remember, we started with 2 of these. But we just applied 200 pounds of nitrogen, or probably about 400 pounds of fertilizer as urea to get this nitrogen into the soil. So this happened all over our field. Flashbacks? All right. Am I still on the camera?
You are.
Where do I get to?
I think you can actually see all the way over there. You can still see that.
Really? Is this it?
I think so.
Cool. Alright, sweet.
The check marks might be out, but most of that
Cool,
is.
that's fine. From chemistry, oxidation states. The oxidation of the electron charge for oxygen is -2. So if we have 3 oxygens at -2, what is the charge? -6. Right, -6 right. If the overall balance of the molecule is -1, what is the oxidation state of nitrogen? +5. See how that works? Yeah? No? Okay. What is the oxidation? What is oxygen? Negative, and we have 2 of those, so that's -4.
Yeah, that's why I don't like that setup that way.
It is. Okay. So then what is the oxidation state? +3. Have y'all started writing, did y'all write this down? Right. Before you get too far ahead, so this is +3, right? What is oxygen right here? -4, correct. What is the oxidation state of nitrogen? +4. For some reason, the way they wrote that in the book, this, like, in order to keep it consistent where you can see the changes, this should be over here. You can add that if you'd like. If not, just understand that we're going to have a change in charge going from positive to negative. All right? What about here? Oxygen. -2. What is the oxidation state of nitrogen? +2. Right? Because our charge is neutral. Right here. Making sense, Nathan?
Yeah, why is the nitrogen different? Like the one right there is +4, the one, I'm trying to think of how to explain it.
Yeah, look at what you mean. Like you're trying to get the nitrogen, like those two, like so, like on the nitrate, you're trying to get +5 and -6 under the charge.
This is because of the valence right here. And so -6 + 5 is
-1.
-1.
So you may not even know
Yeah.
Remember, they're sharing, they have a bond here in those orbitals. When those molecules are formed, all we're doing here is just showing reduction and oxidation. And so when you add oxygen to the system, it's going to take one of those electrons because it's trying to get balanced, and it's -2, right? So it needs to take 2 electrons from someone, like this one right here. This is balanced. They're in equilibrium. Nitrogen shared enough with this to form a neutral molecule. All we're doing is just, it's an oxidation. Actually, this is a reduction going this way. All right? What about here? Oxygen is worth -2. And the oxidation state of nitrogen is +1. Right? Because we have 2 of them. And so the charge here is balanced.
It'll come back to me.
It will.
I remember this, like, it's just gotta come back.
That's why we're doing it. That's exactly the reason why we're doing it. We're gonna go. I'll make sure you know this before you leave. This is part of chemistry. It's part of those 6 processes that we study in soil chemistry. All right. So we got there. Let's jump up here. We don't have any oxidation state on nitrogen, right? It's 0. Put that down there. 0. All right. What about here? Hydrogen is worth +1. What is the oxidation state of nitrogen? -1. Hydrogen is +2. Therefore, nitrogen must be -2. For ammonium or ammonia, and nitrogen is and then finally correct. And what is nitrogen? Negative. Because the charge is plus, right? So we went from -3 through the whole process +5.
Okay, you start over there first, don't you? To the right side?
I did because I wanted to start getting the idea of oxygen. If I had started here, we could have gotten confused there. right? But remember, we need ammonium first. We've got to start with ammonium. And what I'm showing is that oil, y'all remember oil rig? Oxidation it loses, reduction it gains. So in an oxidation, it loses an electron. So in a reduction, it gains an electron. So it becomes more negative. We'll go over it again, but primarily what I wanted, the primary point of this was to understand that oxygen is worth -2, and that influences the valence state of the other molecule associated with it. That is going to influence how tightly a molecule is adsorbed and desorbed from the CEC or the AEC. Like that ties all that in together. I'm gonna do this again on Thursday.
That's fine.
Okay, I mean, like, I see you trying to process it, don't worry.
I'll remember.
You will by Thursday. After Thursday you will, but the nitrogen cycle was a really good kind of tying all of those things in together about all the different processes in that one cycle. And when you can see those in the nitrogen cycle, you'll be able to carry those into any other type of thing that you use. So that's all we got for today. We will catch you all on Thursday.